Hello, I'm Lemarchand, and I will present you electromagnetic sidechannel attack through learned denoising and classification. This work is a collaboration between University of Rennes in France and two teams of DGA, which is part of the French Ministry of Armed Forces. First, I will present you what is eavesdropping, also known as compromising emanations. I will then detail the proposal, present some results, and conclude. So let's begin. Eavesdropping, as always, exists. You can see, for example, in this image, somebody listening at the door. It was more than a century ago. And know that we have electronic systems. There is also a lot of emanations. This is known as a tempest. Tempest is a bench of specifications against information system spying through leaking, compromising emanations. This was previously used by military and diplomatics because it was really expensive and the systems were EV engineering systems, difficult to design and really expensive. Now that the hardware has evolved, it is much easier, and an attackant can design systems with advanced post-processing with just that kind of a laptop. We use such a system in this work. We target electronic emanations of display cables. For example, you have that computer which sends video signal through that cable and to finally display it on the display. That emanates signal that can be intercepted by an antenna and a software-defined radio. And further post-processing can be used to raster the one-dimensional signal, denoise the obtained signal, and finally interpret what is in the signal. The proposal of this paper was to use the learning-based method to go further in the interpretation. So what for? For example, to store only the images that contains useful signal, useful information, or to detect compromising activity in real time and, for example, cut the display. So you have here an example of image that can be intercepted in a good condition, good interception condition. It has a lot of noise, but still you can understand what is in the image. But in some cases, there are hard destructions, hard corruptions, like this one, where a gradient is completely destroyed, or here, where correlated noise come and completely corrupt the image that was completely white before. Hence the need for denoising. So let's go for our proposed method. So first, we propose a special evaluation. The idea is to generate an image with a known content. This content, this image is displayed and the emanation is intercepted, the electromagnetic signal. It is rastered to find back the image. It is denoised and an optical character recognition is done to finally retrieve some characters. And the evaluation is here between a reference and what is finally found in the image. Our proposal sits here in the denoising and OCR parts, and it does use a learning-based method that we present now. So we needed a powerful dataset, and so we designed our proper datasets. First, it contains different characters of different size, different font, positioned in different parts of the image. We store the labels. Then we display and intercept those references. We rearrange them. Using such system with corner detection, shearing correction, and global reorganization of the image. We then align the reference and the intercepted samples. We're using timestamps and validation through QR code. We then patch to have smaller images, and we will see further that it is better for the retrieving algorithm. We have special masking for mask RCNN that is used later. And then we have online data augmentation to get better learning. So the dataset that we obtained is publicly available at its GitHub address. It contains approximately 100,000 of samples. Different archiving parameters were used with 4 types of cables and connectors, 3 antennas, different distances, 3 screens with different resolution, and in every case, a zoom of 100%, which means that the fonts are respected. So we compared 2 types of architecture. So first, we used denoisers to denoise the intercepted image, and further applicate an OCR, an optical character recognition, to evaluate our denoising. So you have some examples here. And our proposal is to have a joint denoising and classification. So we do not have those two steps, and just have one done by mask RCNN. Mask RCNN is depicted by this schematic. So you first have CNN that is used as a feature extractor. You have a region proposal network that extracted region of interest that are aligned with the feature previously extracted. And at the end, you have 2 parts. One part that classify the content of the bounding boxes of the region of interest, and another part that give a mask of the content of the region of interest. So you have that kind of output where each character has a probability, which is a confidence mark on the classification. So the results are here. Here you have a different denoising process. So we see that the better is units with tesseracts that correctly find around 30% of character in the overall evaluation set of characters. And our proposal using mask RCNN has performance of 55% of character retrieve, an F-score of 0.55. And if we go further and do not use Tesseract, so the method that was presented here, we reach a performance of 0.68 in F-score. So these are two result figures. That one presents the distributions of the character in the database. So you have the font scale here, and the number of characters that exist in the dataset for that particular font size. So red is the reference, so it is the database, and blue is the output of our method. So you see that from a font size around 30, we reach a pretty good retrieval before it is complicated. So this is a comparison in precision and recall for all methods compared. And the best of our method is here. So you can see that it is a better method. We can go further and add post-processing to mask RCNN, for example, a text line detection, a hook transform, to find lines of text in the image. For example, here we find this sentence, and using a BTAP algorithm, which is a substring search, we can search into known word and, for example, find secret and raise an alarm to say to an operator, for example, that this keyword has been found in the image. You can extract the characters, for example, here, and even use that system in other applications like text finding in CCTV, for example, here. But still, you can see that there are a lot of artifacts. So the perspectives to enhance this method is to balance the data set with respect to noise and distortions to equally address each noise. This is the content of one of our proposals that you can find in the GitHub and Open Denoising. Another perspective is to enhance mask RCNN. For example, using a more recent backbone like ResNext, who, for example, we can imagine replace the CNN that is used for region proposal network by a recurrent neural network, better take advantage of the bounding box alignments. We could use a model language model to remove confusions, for example, in this image. We could change the classes to objects instead of characters, or study the embedding of that application using, for example, quantization or pruning. You can find more information in our page, that page. For example, you can find the dataset. Thank you for listening to this presentation, and you have here the references that were in the presentation. Thank you.